Okay, now some practical applications. So we will define a little bit the principle of equivalence and time value of money, and then we go through some example of equation of value, and then we see how we can value some cash flows and use time diagrams. Okay, so principle of equivalence, what does it mean? Okay, imagine we have agreed on a accumulation function already, so we think this accumulation function is reasonable. So this is how our investments will grow, right? Over time, over T. So what we are saying here is, with the principle of equivalence, we are saying that people are indifferent on whether they get this amount at this time 1 or another amount at time 2 or a different amount at time 3. This is not the reality, because usually people, their decision on when to pay and when to get their money, it depends on other things as well other than interest rate. For example, they will look at inflation or their needs for expenses, etc. But just for the purpose of solving some interest story in this course, we will hold on to the principle of equivalence. Next is time value of money. The concept is quite related to the principle of equivalence. So we are saying that $1,000 today worth more than $1,000 in the future. So equation of value, what does it mean? So when we want to solve for some interest problems, we will bear in mind the principle of equivalence and time value of money. And usually our interest problems will involve some equation of value. What is equation of value? It is where we equate two different cash flows. So we have cash flow 1 and cash flow 2, and we say they are equivalent. For example, a deposit of 20 and 50 at time 2 and 5 is equivalent to a withdrawal of 100 at time 9. So this is the first cash flow and this is the second cash flow. So if you notice, our cash flow not necessarily be a single cash flow. Like our previous example, this is also equation of value when we are saying this amount is equivalent to this amount, right? But actually cash flow 1 and cash flow 2 can include multiple cash flows. Another example would be two series of investment. Investment 1 and investment 2 are said to be equivalent. For example, we invest X amount every month, and we say that is equivalent to investing Y amount every year. Okay, so this is an example of an equation of value. So we say we have this liability. This liability is due at time 3, 4, and the amount is 2.5 million, and time 7 at 3.5 million. And to pay off this liability, one option is to pay $1 at time 1 X amount, at time 1.5 1.5x, and at time 2 you pay 2x. So we are saying these two cash flow 1 and cash flow 2 is equivalent. So cash flow 2 can pay off cash flow 1. From that you can see equation value for each of the cash flow. You will have the amounts of the different cash flows. So you will have amounts in cash flow 1 and amounts for cash flow 2. And remember, cash flow 1 can be multiple payments. Cash flow 2 also can be multiple payments. See here, equation of value usually have two series of cash flow. Okay, so that series of cash flow will consist of the net amounts. So cash flow 1 will have their net amounts. I say amounts because, as I said, it can have multiple payments, right? And cash flow 2's net amounts. Also, it will involve timing of those cash flows. So the timing for the cash flow 1 and timing for cash flow 2. And then there is also interest rates. So both of our series of cash flow should should follow the same interest structure. So maybe we can say they should follow the same accumulation function. For our previous example, only this part is missing. So we know the timing, we know the amounts for cash flow 1, we know the interest rate, but we don't know this. So usually in an interest problem, you have the other infos but not one of it, so you need to solve for the missing information. So how do we solve? Like for example, in this case, when we are equating, where are we valuing these two cash flows? So this one, accumulated value for the liability, is valued at time t. What t should we use? The answer is we can value at any t. It doesn't matter. Equation of value can be valued at any t. Why is that so? This is true because they both, this cash flow and this cash flow, follow the same accumulation function. So let's say we are evaluating at time 1. AV1 for the cash flow 1 is equals to AV1 for cash flow 2. So if we want to evaluate at time 2, you will find the future value, right, to accumulate it at time 2. This one, if you find the future value, you are also following the same interest structure. So AV2 is also for 1 is also the same as AV2 for 2. Understand? Because it follows the same structure. So the comparison time doesn't matter if the interest rate for the two cash flows matches. However, there will be cases, there will be examples throughout your course where you are comparing two different cash flows that follows different accumulation structure. For example, one is using compound interest and one is using simple interest. So in those cases, if you are doing equation of value, you need to specify the comparison time. So you are saying, okay, these two cash flow are equivalent at time 10. So only at time 10 they are equivalent. If you want to compare at time 9, they are not going to be equivalent because they follow different interest structure. Okay, so this is just going a bit deeper. So as I said just now, cash flows can be multiple payments, right? Actually, cash flows also can be discrete payments or continuous payments. So before we have been dealing with discrete payments, but there are also continuous payments where it is like a stream of income, stream of cash flow that come in, or it is like an income or an outgo that is momently. So this one, I'm not going to focus on its calculation yet for this chapter. For this chapter, we will just focus on valuing cash flows with discrete payments. Okay, so this is generally how we value cash flow. So as I said just now, we value at a comparison time. It doesn't matter what comparison time we choose, especially if both of the cash flow is following the same interest structure. So for all of the discrete payments that we are considering, those payments will be paid at many numerous time t. So maybe as for this example, our cash flow 1, the t is 3 and 7. Cash flow 2, the t is 1, 1.5 and 2, right? So this t can be before or after the comparison time. So if it comes before, if the t is before the comparison time, we will need to find the accumulated value. And if the t comes after the comparison time, then we will need to find the discounted value. Okay, understand? So no need to worry too much on this formula. let's look at an example. Okay, let's see an example. Evaluate the following cash flow at time T3 when the force of interest is a varying force of interest. So, okay, first, is the $100 and $200 a continuous or discrete payment? So yeah, it's a discrete payment, right? And secondly, let's try to evaluate. So you want to evaluate time 3. So for this single cash flow, what do we do to evaluate time 3? You need to find the accumulated value. For this one, you will need to find the discounted value. So let's do it. For the first one, 100 e to the power of, you have to integrate between 1 and 3. So the delta 0.02 t dt plus another one is 200. You need to find the present value. So when you do the present value, you need to put negative here. And so the negative is between 3 and 4. So you do 3 and 4. Then you put here 0.02 t dt. So if you calculate this, you will get 108.33 plus 186.48 equals to 294.81. Okay, so now you have 294.81. That is the value at time T3. So now evaluate the same cash flow at time 2. 1, using the same method as above. So using the same method as above, using the same method as above, you can do it again lah. Okay, using the same method as above, but now at time 2. So now you are accumulating 1, and then this one you are discounting for 2 years. Okay, so when you do the above, same like above, you get the answer. The answer will be 280.53. Another way to do this is to use principle of equivalence. So before this, when you evaluate A at time 3, you get 294.81, right? This one. So if you want to evaluate to time 2, you just bring this to time 2 with the following the interest structure given. So this fund follow this interest structure, right? So how do you do it is you do 294.81, you discount it 1 year. So how do you discount it 1 year? E power of negative, so this one is between 2 and 3, so 2 and 3, 0.02 t dt. So you will get 280.43 juga. One is you are using the you are using the normal method, you do 1 by 1. One is you are using the principle of equivalence. Okay, which would be a good choice for comparison time? So now we just have one cash flow, right? Cash flow 1. But let's say if we are doing an equation of value, we want to compare with another different cash flow. We are saying that they are equivalent. So we want to choose a comparison time. What is a good choice of comparison time? For me, I would choose 1 or 4, because by doing that, I just need to do the present value and accumulated value for just 1 instead of 2. So I would do that. Before this, I already used some time diagram already. But yeah, let's try to see how this can be done. It's very useful to use time diagram because you can see, especially if a cash flow involve many timings. So usually this is how we do it. The amount, we put it either on top or at the bottom. But if we are talking about two different cash flow 1, cash flow 2, it's better to put one at the top and one at the bottom, right? So that you don't confuse yourself. And then you will put the time under the timeline, and also you can write like this to show what is the interest rate that is applicable. Right. And then this arrow is if you want to really indicate to yourself where are you evaluating your value. So, or you want to make the comparison time clear. So now you are valuing everything at time 0, so you just use an arrow. So it is calculating, so it is doing an equation of value. So you see, x plus 2x discounted to time 0 is equals to 1000 discounted to time 0 plus 2000 discounted 5 years to time 0. So you will solve for x by doing this. Okay, this one is when we are valuing uncertain payments. So here we have an example where the we could get a payment of 100 at time 0 and a payment of a 200 at time 2, but there is a probability to get those. It's not 100% chance. So to value this cash flow, you will need to consider three things: amount, timing, and the probability. Previously, we just consider amount and timing, but now you have to include the probability aspect. Okay, that's all. Some new challenges in a interest problem or equation of value. So the first problem is when we have unknown time and we need to find what is the time involved. So suppose that you deposit $500 in a fund at 4% effective. How long will it take for the fund to grow to 1,500? So you start with 500, but when it accumulates with a constant interest rate, how many years do you need to reach 1,500? So you don't know t, unknown time. So if you rearrange, you will get the second equation. So now what do? You need to use log. You log both sides. You log this side and also you log this side. So you get log 3 and equals to log 1.04 to the power of t. And then so by doing that, then this one you can bring to the front, right? So then you can solve the equation. So remember, you have to play with log if you have unknown time problem. Second would be when you have unknown interest. So this is the timeline for this question. You have a payment of $1 and $2 and $2 at the respective time. We run one. What is the interest rate, the constant interest rate that will apply to get accumulated value at time 2 of 4 ringgit. So when you have to write down the equation of value. So the first deposit you will need to accumulate 2 years. That's why you do like this: 1 times 1 plus I to the power of 2. And then the second deposit, it will accumulate 1 year. So that's why the second deposit of $2 will accumulate for 1 year. 1 year. So it will equals to 4. So you can solve this using quadratic equation. So this is a simple problem, but as you can see, if you involve more single deposits, then this will lead to a more complex polynomial. So maybe something to the power of 3, something to the power of 5, something to the power of 8. So can be very complex polynomial. So usually in our exam, I will just give, if I want to give something with an unknown interest, I will give something that can be solved in an exam environment, so it wouldn't involve too much complex polynomial.